Today we are going to have a look at how to use Maple to do integration and its applications. So we just opened the tutorial. It doesn't matter the version of Maple, if it's Maple 16, Maple 17, more or less they are the same. Okay, so we are going to be looking at how to compute antiderivatives, also the definition of a definite integral using the Riemann sums, and we are going to see how to compute the area between two curves and the area bounded by a region. So let's start with the computation of antiderivatives. So we say that a function is an antiderivative of f if, when we differentiate this function, we get the initial function. So how do we compute antiderivatives using Maple? We can do it in two ways. We can do it using the palette. You can find it in the expression palette, and then using the command in. So remember that Ctrl-J, Ctrl-K adds new lines, and then using F5 we can change the mode. So we press F5 anytime we need. So let's start computing an integral or an antiderivative using the palette. So first we're going to define the function. If we don't remember how to define functions, we can use this button here. F, variable is x, and then we introduce 8x to the power 3 plus b times x squared plus c times x. This should not be a c squared, but a c times x plus d. So now that we have the function, we can indeed see that f of x is what we needed. Let's change to math2d and compute the antiderivative of f of x. Remember the tab button, and now we just execute. To execute the line, you can place the cursor wherever you want. You don't have to go to the end. So this would be an antiderivative of the function we had. So now let's see how to do it in Maple 1D. We just move up. Sorry. Let's copy it into the mode. And now we cannot see this, but what we do is right click, 2D math, convert to 1D math. And we see that when we use the palette, what we are doing is using the int command, the function, comma, the variable. Okay, so how we can check that this indeed is an antiderivative? So just by differentiating this function and see that we recover the initial one. So we're going to do it using the context-sensitive menus, differentiate with respect to x, and we see that we recover the initial function. So an antiderivative of a function is a function that when we differentiate it, okay, using the diff command, we get the initial function. Now, with Maple, it's really easy. We can use the in command, and Maple computes almost any antiderivative that can be computed analytically. But now let's see another thing which helps us compute the antiderivatives step by step. So let's see how to do it step by step, and this is really helpful when you are studying. So let's first define the function f5. We press F, tab x, and now we introduce the function we are given, x squared times 1 minus 2 times x to the power 5 all to the power 3 divided by 4 plus x squared divided by 5. Let's see if we have the function we are given, x squared divided by 4. It's the same. Okay, so now let's use this tutorial to compute the antiderivative step by step. So we are going to go to Tools, Tutors, Calculus Single Variable, Integration Methods, as shown here in the tutorial. So, before entering, just to avoid to write again the function, we just copy this and we just open again the tutorial. We paste the function and we start. So here we have to compute this integral, and we can ask Maple to get a hint to get help. So it says notice the sum in the expression. So we have here a sum. We are going to divide the integral in two parts. We press sum. And now let's see what Maple says. Are there factors in the expression that are constant? So we have constant factors that can be taken outside. If we do next step, you will see that we have 1 divided by 4 that is getting outside. Hint, try rewriting this. So now Maple says that you compute this, you expand this term, next step. So everything got expanded. Next hint, notice the plus. So now it's going to divide all these terms, all at once. Again, are the constant factors. So again, we are going to get the constants out. Maybe, no, all together or one by one. Okay, and now it has integrated this. The power rule again, it has constant multiple, it has taken outside some constants, and then you go and go and go and go, and everything gets computed. Okay, so this was a quite simple integral. It was large, but it was quite simple. You can see that. However, all the steps that Maple has done. Remember that if you want to get the results into Maple, you should copy here and then close the tutorial and paste it. Okay, so now you have it here. Okay, just all the things that we have done. So now let's open it again and let's try to do another integral. So x times the exponential of x. If we now get hint, Maple says notice the multiplication in the expression, and because we have an x times e to the power x, and if we do next step, what we get is that the part rule has been applied. So you should know that in order to compute this integral, you have to apply the parts rule and then again the exponential rule. This is a basic integral, so it's done. Okay, so remember that we can copy this, close, and we get the results. Okay. If you don't get the results, since we have copied it, you can copy them, and then you will get all the steps. Okay. Now the last one, x times the exponential, of x squared. We get here and it says, can you do a change of variables? Okay. Maple is suggesting that we do a change of variables, but Maple is not saying which change of variables. So if we make a change, he asks us to make a change of variables, okay? But we have to enter the change. And if we do next step, Maple does the change, but it does not say which is the change. Of course, if you see that x squared is replaced by u, you can imagine which is the change in this case. But this is really helpful, but Maple does not say all the details of the things that he's applying. So let's now see another way where Maple helps us do integrals, but where he tells us exactly what we have to do. Okay, so just to check the results, this is useful, and let me delete this. But let's see another way which is far more useful, which is using the hint command. Okay, so the first thing we have to do is to look at the help of this command. And as always, look at the examples. As you see, you have 2 lines before the first example. So this is like the with package. So we have to introduce these 2 lines in order to be able to use the hint command. So we should copy this and then paste it. But you can see that you have it already in the tutorial, so you just have to execute the lines. So press enter to both lines. Don't forget to press enter. Okay. So now we have loaded the packages that the hint command requires. So now let's see how to compute this x times e of x integral using this hint command. The first thing we have to do is to introduce the integral without a capital I. If I use the small I, I get directly the result, but now I don't want to get the result. I want to do it step by step, so I introduce int with a capital I. And now I ask, help me with this integral. And it says, you have to use parts where one of the function is going to be x. Okay, now what we can do is, Maple is not only telling us what to do, but we can use the rule command, okay, where this is this, okay, and we apply this rule to the integral a, and we say that if you do parts one time, okay, you should get this result, and then you should continue using the hint command, but you can also directly, in any of the steps, say value of a, and you get the final result. Okay, so let's see how to use this in other examples. So compute the following antiderivatives manually. So let's start. The idea here is that since we already executed these lines, we don't need them, but in any case, if you had to do an exercise, you should need to place these lines, execute them, and now do the exercise. So let's define the first integral. I1 is going to be the integral of f times the exponential of x squared with respect to x. Okay, you can also do it with the palette if you want, and then change the small I for a capital I. Okay, now that we have the integral, we ask for help. And Maple tells us that we need a change of variables, but look at this. It does not only tells us that we need a change of variables, but also it suggests which is the change we should apply. So the change should be u equal x squared. Now we would do this by hand and then check if we have it right by applying this rule to the integral I1. Okay, so Maple has applied substitution with this change of variables, okay, and if you do it, you should get 1/2 of e to the power u with a new variable. Now we can continue by asking for help, but now we want to get help from this 1.15 equation. So we press Ctrl L or insert label 1.15 and we ask for help. Of course, Maple now is telling us that we have to take this 1/2 outside, so we apply this rule constant multiple, again Ctrl L with respect to 1.15. Now we have the 1/2 outside, and we can go on and now ask help for the equation Ctrl L 117, and it says this is a basic integral, the exponential of u, you should know that. So apply the rule of how to integrate the exponential function at which expression, again 117, Ctrl L 117. So we get this, which is not the final result because the first integral was with respect to x and now we have a u. So again, we ask for hint for the equation 119, Ctrl L, and we get the revert command. Of course, if we do a change of variables, we have to revert it. So if we apply the rule revert to the integral 119, we finally get the final result. Of course, if you do the integral with a small I, okay, let's copy this. Oh, we change it by a small I, you would get the same result. Okay. What is the advantage? That you can keep on doing steps one by one and check that everything that you've done is correct. So now let's see what Maple's tells us about these integrals. Let's go to the I3, square root of 1 minus x squared. So we start by defining A3, like the integral of square root. If you don't remember, you can use this, of 1 minus x squared, I believe. Let's check, square root of 1 minus x squared. And now let's see, I don't know how to do this integral, so I ask Maple, getting help. And here Maple tells us 3 different ways of getting the final result. So in this case, you can try all the options and see which one looks best for you. For instance, if we apply the change x equals sine of u, we should integrate after that an integral of sinus of u to the power 2, okay, which is not quite easy. Let's see what happens if we apply the second change. So when we have this, we apply it. In this case, after the change, you should know how to integrate a quotient of polynomials. And if we apply the third rule, you get also a quotient of polynomials, but maybe more complex than the previous one. So Maple tells you all the options, and then you should check which is the one that is best for you, and then you can do it and check the results. If you want, for instance, to know how to compute another integral, cosine of x times e to the power x, so you came here, I don't know, I'm going to use a2, integral of cosine of x times the exponential of x. Then you go and ask for help. This integral is solved by parts. And for instance, another 1, 2, 3. You can also check this sine of square function. So let's put another integral which usually you don't know how to solve. The logarithm, if you ask for help, you see that you have to apply parts. And then you can do this if you want, rule on I5, and see what you should get after applying the parts command. So, for instance, another one which is not cosinus, which is not standard. If we ask for help, we also get that this is done by parts. So you could also apply this and see what would be the result. And you should arrive to the integral of something like this. Okay, so this is really, really helpful while you are studying how to compute antiderivatives, because you can go step by step and check everything you need to check. Okay, if you, for instance, you can start with this simple one with this change of variables and then go to more complicated integrals. So I suggest to use the hint command rather than using this tutorial, because this tutorial does not say step by step. Well, here if you do it, okay, now with this 17 version, Maple, I can see that it also tells us what she has done exactly with the change. But when you look at the window, Maple was not telling us which was the change. Okay, so this at the end was faster than what we did here, but in the tutorial, Maple didn't tell us exactly what was the change. Okay. So now that we know how to compute antiderivatives step by step or directly, let's see how, or the meaning of a definite integral. This means that it's an integral which is going to be computed between a and b, between two values. Okay. And the important thing is the relation between this definite integral with the area of the function. Okay? And the idea is that the area between a function and the two straight lines x equal a and x equal b is defined as the integral between a and b of the function x. Okay? So the integral of this function between a and b is going to be the area below this function. So in order to compute a definite integral, it's really easy with the palette. So if we just want to get the value, remember to use the tab button to change from one expression to the other. So this would be the value of this definite integral. Remember that with the right hand button, approximate to 10 decimal places, you have the result. And then you can see how we do it in 1D just by copying and pasting and use 2D math, convert to 1D. And the idea is that we use the same in command, but now instead of comma x parentheses, then we add equal, and the lower interval column dot dot the upper limit. Okay, so it's between 1 and 2 or between 10 and 20, it doesn't matter. Okay, so here you put the syntax and you get the same result. So now you know how to compute this area directly. Let's see what is the idea of, or the intuitive idea of why this integral gives us the area. So you can look at this four subsection by yourselves, but we are going to move directly to the approximating tutor because it does the same thing. Okay, so now, as we have seen, the integral, let me just do it now for you. This is the integral we want to compute. Okay, and numerically this should be a 0.4596, etc. Okay, so now let's see how we can check that this number is related, or how we can see that this number is related to the area. So we will go to the approximating tutor. So we go to Tools, Tutors, Calculus Single Variable, and then we are going to go to Approximate Integration. Okay. If you do this, you can see that Maple is opening the Approximate in tutor, and we have a function. Here, our function is sine of x, but we are working between 0 and 1, so we make display. And now what we want to find is, let me change this. We want to find the area under this curve. Okay, so imagine that you don't know how to compute it. The first idea is to compute areas which we know how to compute and relate them with the area below the curve. So what the first person did was, we just changed this to upper, is to try to do rectangles, for instance in this case 2 rectangles, which taking as height of the rectangle the maximum of the function at this interval, and the same for this other interval. Of course, computing the area of a rectangle and then adding this other area is really easy. So in this case, if we compute the area of these 2 rectangles, we would get 0.66. And since we are taking the maximum, we know that we are, of course, being above of the actual value of the integral, which is the area below the curve. However, what we can do is to do more rectangles, and we now see that the area of the rectangles goes down, is 5.56 or 56, which is approaching the actual area. So if instead of 10 intervals we take 10 intervals, we get an area. If we add all the areas of the rectangles, we get an area of 0.5. And if we keep increasing the rectangles, we can see that we are, in the end, converging to the actual area we want to find. So what we say is, what is the area below the curve? Is the limit of the areas we obtain as we tend to do the number of intervals to infinity. So if I say 100 intervals, you can see that we get a pretty good result. So we now have 200 intervals, and the idea is that since in each interval we are taking the maximum, this value is going to approach always the area from above. Okay, so we can go for 300. Okay, don't put a lot of pressure to Maple. You can try with 500. Okay, so you can see that each time we are approaching the area from above. Now let's see what lower does. Lower 2, it means that now we are going to take the minimum of the function as the area, the height of the interval. In this case, if we add, this is a 0 area and this rectangle has an area 0.23, so we are approaching the area we want to find from below. So if we increase the number of intervals, we have 4 now. You can see that this value is increasing. we can use 10 again, 0.41, 30, 0.44, we can add up to 100. You can see that all the values are always below the exact value we're searching, but if you increase it, so this value tends to this. So we say a function is integrable when, as we do the limit when the number of intervals tend to infinity, we tend to a number, and this number is the value of the area of the function, which is defined as the integral, okay? You can also take rectangles of different height or altitude. In this case, we take the midpoint, and you will see that how fast we would reach, we will approach the actual integral. In this case, with only 10 rectangles, we have the three first decimal places, 20, 100. So you can see that with 100 rectangles, we already have the first 5 decimal places. But as you see, in all the cases, as I increase the number of rectangles, I'm tending to the same number. This is because the function is integrable, and if I do the limit, I would get the value of the integral, okay? So now I have 100, it's going to take quite a lot of time, so it's going with this number, okay? So the idea is that a function is integral, or integral in the sense of Riemann, if when we take the rectangles, all the values as the n tends to infinity, as the number of intervals tend to infinity, we all converge to the same number. Do you think that we are going to compute these integrals making 100 rectangles and then adding all the areas of the rectangles? Of course not. Hopefully we have the Barrow rule, which helps us computing areas or integrals, definite integrals, without having to do rectangles. But the idea is that the definition is the value of the integral is the limit when we take infinite rectangles and we add all the areas, okay? So now that we know the intuitive idea, okay, of course with Maple, as I have told you, you already have done this, we just compute the integral by using the palette or translating it. What is the Barrow rule telling us? I'm going to show you the Barrow rule. Let's convert this to 1D. So what is the Barrow rule telling us? That if we want to compute a definite integral, I just have to compute an antiderivative. In this case, the antiderivative is minus cosine of x. And now what I have to do is to evaluate minus the antiderivative at the ending point minus the antiderivative at the point 0. So in this case would be, this is a 1, minus 1 is plus 1 minus cosinus of 1, okay? So instead of computing the area of the rectangles, what we finally do is we compute an antiderivative, and then we evaluate the function at minus 1 minus the function at 0. This, I don't know if I will be able to do this now. We usually show this putting a bar here and putting a 0 down and a 1 up, okay? So this is the Barrow rule, which allows us to compute or to easily compute the values of definite integrals without using rectangles. So now let's move. We have seen the relation between the area and the definite integral in the case of positive functions. Let's see now how to compute areas, okay? So let's start with the area between two curves. So imagine, in order to compute the area between two functions f and g, what we have to do is, in a region between a and b, what we have to do is, first, compute the intersections, the points where the functions intersect. And now determine the subintervals where f is larger than g and where f is smaller than g. Why? Because in the intervals where f is larger than g, f minus g is positive, and we have the area is given by the integral of f minus g. And in the regions of where f is less than g, g minus f is positive, and then the area is the integral of g minus f. Okay, so let's do this exercise. We have it more or less done. So with plots, we define the two functions, and now with plots, we are going to use this command in order to make two plots at the same time. So we make the plots A and B, and now we display them. So we are asked to compute the area between these two functions between 0 and 6. So we are asked to compute this area plus this other area up to 6. Okay? First thing, we have to compute the intersection. So in Maple it's really easy because we can say solve the equation f equal to g, and it says -1 and 3. Of course they intersect at -1 and at 3. -1, we are not interested in this point because we are looking at the function between 0 and 6. So now, between 0 and 3, the function which is above is the blue one, which is f. So between 0 and 3, we should integrate f minus g, which gives us a positive number of 9. And between 3 and 6, the function which is above is the red one, which is g minus f is the positive one. So we integrate it and we get a 27. And finally, the total area is going to be 36. Okay? So remember that anytime you are asked to compute the area between two curves, it's crucial to compute the intersection, because all the values you have to add when you are computing areas, they should be positive. You cannot compute the integral between 0 and 6 of f minus g or g minus x because you are going to be compensating the area. So let's do a different exercise. Following one, exercise. Compute the area determined by the function f of x equal to x squared minus 1. Okay, just a question of style, but you don't need this. Between x equals 0 and x equals 3, for instance, okay? Now let's do this exercise. We just have one function, but it should be done in a similar way. So f5, sorry, not now. f5, we define the function f(x) x squared minus 1. f5. Now we need to make a plot, but since we only have one function, we just can do it using the plot command. Plot the function between 0 and 3. And we can see that we have an intersection. The function is not positive. If the function is positive, the integral should be just the area coincides with the integral. If the function is negative, the area is minus the integral. So in this case, we need to compute this integral and change its sign and compute this integral and as it stands. Okay? Now, in order to compute the intersection, in this case you can see it clearly, which is 1, but we would say solve f of x equal to 0. So we ask Maple to solve to compute the intersection where the function is going to vanish. So we have -1, which is outside our interval, and 1. So this is the intersection point, and now we have two different areas, A1. Between 0 and 1, the function is negative, so we should compute the integral of minus f of x. Now you see that we get a positive value. If we remove this minus, this integral is negative since the function is negative. So the area is going to be given by minus this integral. And on the other hand, the area of the second part between 1 and 3, since the function is positive, we just have to compute the integral. Okay, so remember that if you just have a function, you have to find the intersections with the axis and compute the integral of minus the function in the areas where the function is negative and the function in the areas where the function is positive. So the total area would be A1 plus A2, which is 22 divided by 3. And if you have two functions, you should compute the intersection between the functions and then integrate always the function above minus the function below, because we need to get positive numbers. Okay, so this is how we would compute the area between two curves. And now let's see the area bounded by a region. The idea is the same. Now here we have three functions, but they don't give us the functions directly defined by y equal to. So we should isolate the y. In the first function, we get that the f is going to be y is equal to be x divided by 3. The second one, if we isolate the y, we get minus x, so x is minus x. And in the third function, we take the 7x to the other term, so it's 24 minus 7 times x divided by 3. So these are the three functions. We already have the plots prepared. We execute all the lines. And we have these functions. So we see that the g function, the blue one, always goes below. The brown one goes on top between 0 and 3. And the magenta one or pink one goes on top between 3 and 6. And the area we are asked for is the intersection of these three curves, which is this region. Okay. So first of all, we need to compute these intersections. Of course, in the plot, we see that they are 0, 3, and 6, but maybe instead of 3, it could be 2.90 something. So we should compute the intersections. How we do this? We solve the equations f equal to g. So f is going to be equal to g, brown and blue, it at 0, x equals 0. Okay. H equal to g, pink and g, it's going to be at 6. And h equal to f, it's going to be at 3. Okay? So we check that indeed these are natural numbers. And now we have to compute the area. And you can see that this area is formed by two parts. If you can place here a straight line, you have the area of this triangle and the area of this other triangle. So now let's do it. A1. The first area, function above, f of x, minus function below, j of x equal from 0 to 3. So we get a 6 for the first area. Now Ctrl J, F5. The second area, A2, we are going to integrate from 3 to 6. So we integrate from 3 to 6. Which functions? Pink one, h, minus blue one, f. So h of x minus j of x. So we get a 6. Even though it's not quite clear in the plot, these two triangles have the same area, which is 6. So the total area is going to be A equal to A1 plus A2, which is going to be 12. Okay? So the important thing to remember is that when you are asked to compute areas, you don't compute integrals directly. If you have a function, like here, you have to compute the intersection with the axis and then see in which places the function is negative and in which places the function is positive. If you have two curves, you have to compute the intersection points and see which function is above and below. And it's really, really similar to where you have a region, because you also have to check which is the function above and below. In the regions, you have to divide. your initial vision. Okay, so just to end up, remember that in all the tutorials you have the self-evaluation exercises which you should try. Here you have the computation of some in antiderivatives using the palette directly and using the hint command to see all the steps. And then here you have 3 more exercises of computing areas that you should try to see what is the value and everything. So with these exercises we are done, so the session is completed.